All right, tonight what we're going to be talking about is heat. What is heat? Well, heat is caused by the collisions of particles, and it's that transfer of energy from one particle to another through these collisions. The symbol that you use in any mathematical equation is going to be Q. So when we see our equations later on, Q represents heat. The unit you always use for this class will be joules. We abbreviate its symbol as a capital J. And then what's interesting to note about heat is that it always goes from hotter to colder, or something with a higher thermal energy or temperature to something with a lower thermal energy or temperature. And what that means is, like, if you're holding an ice cube and it feels cold, what's happening is your heat is actually leaving your body and going into the ice cube. The ice cube's coldness is not entering your body and making you cold. It always is heat leaves, okay, and goes to something that has a lower thermal energy or lower heat. All right, here's an example of a heating curve, which we developed during the Icy Hot lab. What you want to note is that it is absorbing energy. How do you know that? Because your temperature is increasing, and temperature is directly related to amount of energy. So if it is absorbing energy, we know that it is an endothermic process. As we noted during the Icy Hot lab, anytime there's a temperature increase, we are in the same state of matter. There are 3 states of matter shown on this heating curve. So what that means is that we're going to be using the solid, liquid, and gas. The state of matter that's associated with the least amount of energy is a solid. So this would be a solid, then comes a liquid, then comes a gas. During these plateaus, we are undergoing a phase change. This would be a solid to a liquid. This would be going from a liquid to a gas. Solid to liquid is known as melting, and liquid to gas would be called boiling, or we'll say it as vaporization. The cooling curve on the next slide is basically a mirror image of the heating curve. If we look at our temperature, it is going down throughout the process, which means that we are releasing that energy. So it is considered an exothermic reaction. We still have those 3 states of matter where they're going to be doing that temperature decrease in this case. So the energy, the state of matter that is associated with the largest amount of energy would be a gas. So this would be a gas, then comes a liquid, then comes a solid. Right here, this phase would be a liquid to a solid, and then this would be a gas to a liquid. Gas to a liquid would be called condensation, and then liquid to a solid would be called freezing. There are 3 basic units that you're going to need to know for energy. The first one that I'm going to talk about is actually the joule. The joule is the one that we're going to be using for all of our mathematical equations because it's a scientific one, and we use a capital J for its abbreviation. The one you're probably familiar with is a calorie. What is interesting to note is that this is a little calorie, so that should actually be lowercase. And what they did is they figured out how much energy it takes for 1 gram of water to be raised 1 degree Celsius. And they did a lot of experiments and figured out the exact amount, and from that they defined that as 1 calorie, which symbol is a little CL. What you're used to with calories is actually a food calorie. And what is a food calorie? A food calorie is 1 big CAL. Okay, this is capitalized. And so a capitalized calorie is equal to 1,000 little calories. So basically 1 food calorie can raise 1,000 grams of water 1 degree Celsius. And what's also interesting to note is if you write down this conversion and then you convert it into big calories or food calories, we would need 4,180 joules to equal 1 food calorie, 1 big cal. And so what we're talking about is what the units of energy that we're using is they're very, very small amounts of energy compared to what we're familiar with food calories. All right, so let's do some conversions. First one is we're going to go from joules to calories. So I know that there's 4.18 joules for 1 little calorie. So when you multiply that out, you get 11.96 little calories. Rounded to the right number of sig figs, which would be 1, would be 10 calories. That's it. The next one we're asked to do is convert 34,000 joules into kilojoules. There are 1,000 joules for every 1 kilojoule. So multiply that out and you get 34 kilojoules. All right, so you're going to be expected to do a lot of heat equations and calculations to determine how much heat did it take to do this part, how much, what final temperature, if you use this much heat, could you do, where could you get up to, and stuff like that. I'm going to skip the first part. I'm going to talk about the equation first. And this is a general equation that you're going to be using, which is Q equals MCAT. MCAT or MC delta T. Q is your heat energy, and that unit is going to be joules. M stands for mass, which needs to be in grams. C we're going to talk about in a second, which is your specific heat. And delta T is your change in temperature. Note that first off, you can be in Kelvin or degrees Celsius for this, but the change in temperature always has to go final minus initial. I will refer to this equation as MCAT. And you will use this equation whenever on the heating curve you are undergoing a temperature change. Why? Because if you weren't undergoing a temperature change, this would be 0, which means you would be using no energy, which is not true. The C value is your specific heat, and what it varies depending on what substance you're talking about and what state of matter that substance is in. These are all constants, so we will always give them to you on every single problem, unless that's actually the variable you're solving for. And what they did is they did a lot of experiments, and they figured out how much for that particular substance, how much energy do you need to supply in order to raise it one gram of that substance 1 degree Celsius. Okay. So looking at some specific heats, what is it say lead has 0.13 joules per gram degree Celsius. So what does that mean? We needed to put in 0.13 joules of energy to raise 1 gram of lead 1 degree Celsius in temperature. So when it asks which one will heat up faster, lead or water, what you're going to do is look at these specific heats. Water is 4.18, lead is 0.13. So that means that lead, you need to put in 0.13 joules to raise it 1 gram, 1 degree Celsius, and water, you need to put in 4.18 joules. So water takes a lot more energy in order to raise it 1 degree Celsius if it's the same amount in mass as lead. So if we put these both on, let's say, under a flame, water would take longer than lead because you needed to put it more energy into it in order to raise its temperature. So let's do a calculation. First off, you want to figure out which calculation you're going to be doing. Because there's a temperature change, I know I'm going to be using Q equals MCAT. I also am going to try to look through these problems and see what variables I know. So 434 joules, that's going to be my Q. 3.4 grams, that's going to be my mass. 21 degrees is going to be my initial temperature, and 85 is going to be my final temperature. So my Q is 435 joules. It's 435 joules. My mass is 3.4 grams. My C is what I'm trying to solve for. And my delta T is final, which is 85, minus my initial, which is 21. When we put it all together, I get 64 for my temperature difference. Okay, my X, see, and then 30.4 grams, 435 joules. I'm going to consolidate and put 3.4 times the 64, so that's 217.6 times X equals 435 joules. And then now I'm going to solve for X by dividing by the 217. I get X equals 0.999, which rounded to the 2 sig from the problem would be 2.0 joules per gram degrees Celsius. So the specific heat is 2 joules, 2.0 joules. All right, what we just talked about was when you have temperature changes. The next equation, which is the final equation, is what do you do when you're undergoing phase changes, which is this flat line. And there's one equation and 2 different constants depending on whether you're down here or whether you're up here on the graph. And the equation is Q equals HM. Okay, H is going to be a constant. And depending on whether you're down here or up here, it's going to either be called heat of fusion or heat of vaporization. Q is still your joules and or energy, and M is your mass, which is in grams. So if you are in the freezing or melting point, you're on this part of the first phase change, and that H is known as the heat of fusion, which is the amount of energy required to melt or freeze a substance. Okay, it's good to note water heat of fusion is going to be 334 joules per gram. Okay, but that is for when it is melting. If it is freezing, it's an easy switch. All you have to do, so this would be melting, all you have to do is make it negative 334 joules per gram, and that would be for freezing. I would write these down because we're going to be using them, but we will give them to you on a test or on quiz or on homework package, what these constants are. All right, then heat of vaporization. So heat of vaporization is when we're on this heating cooling curve. It's when you are right here, which means that you are either evaporating or vaporizing it or condensing it. The one for water in this case, and notice that the formula is the exact same. The one for water for heat of vaporization is 2,260 joules per gram. That is for when you are vaporizing. So when I am trying to condense it, it is going to be negative 2,260 joules per gram. So let's just do a problem. It asks how much heat, so I'm asking Q, is required to melt. Melt would mean that's a phase change of 25 grams. So that's my mass. So I know I'm undergoing a phase change. So I'm going to do Q equals HM. My Q in this case is what I'm solving for. My H, because it is water or ice, is going to be 334 joules per gram. I'm going to multiply that by my mass, which is my 25 grams. When you figure this out, it's 8,350 joules, which means rounded to the 266, 8,400 joules. So which equation would you use? Well, anytime you would want to do a delta T or a temperature change, you would use your MCAT formula. So this would be MC delta T, MC delta T, MC delta T. This one, anytime you are undergoing a flat line, you're going to be doing a phase change, which is your HM formula. The phases are going to be changing when you are flatlining, so this would be your delta pH. And then the temperature changes would be up here, so this would be your delta T, anytime you notice that you have a temperature.